Hey, what's up, guys? Today I'll be going over how to find net charges on amino acids within certain pH environments. Now, in order to answer these types of problems, it's really important that you first understand certain concepts such as the Henderson-Hasselbalch equation and relationships between pH and pKa. So the question we have is, given the pH of the environment is 4.8, what would be the net charge of glutamic acid given the pKa of its carboxyl, amino, and R group is 2.2, 9.7, and 4.2 respectively? I always like to reorganize the information given in the problem so that it is easier for me to use. Since the amino acid we are analyzing is glutamic acid, a derivative of glutamate, I would first draw out the amino acid structure and then label each group with their respective pKa.
Another thing is that I draw each group in both its forms. For instance, the amine group is written as NH2/3 because at this point, we don't know whether it's the NH2 no charge or the NH3 with a positive charge. And this is the same for the other groups, such as the carboxyl and the R group. We don't know whether or not it's a no charge or a negative charge. As we work through the problem, we will find out exactly what charge it is.
So finding the net charge of an amino acid requires you to simply add up all the charges on each ionizable group, which in this case is just the amino, carboxyl, and glutamic acid R group. The key step is being able to deduce the charges that belong to each group. For me, I always use this trick to find charges. I first write the pH and then I set up a range of plus and minus 2. These regions will be compared to the given pKa values to determine whether or not the charges are full or partial. If the pKa is inside the pH range, then the group will have a partial charge. If the pKa is outside the pH range, then the group will have a full charge. Now, given the charge is full, meaning it is outside the pH region, the side that the pKa is on relative to the pH will also determine the type of charge the group will have. With this example, I will write out the pKa values in red and the pH values in blue. The pH given is 4.8, so I write that number in the middle. Subtracting 2 from that number will give us 2.8, and adding 2 to that number will give us 6.8. This is now the range we will use to compare with the pKa values. Starting with the carbonyl, it has a pKa value of 2.2, so we would write that number outside the range to the left and also label it as a carbonyl because the type of group it is will affect the kind of full charge it gets. The amino group has a value of 9.7, so we would write that number outside the range to the right. The R group, however, has a value of 4.2, which is within the range. Overall, we now know based on the regions that the carbonyl and amino group have full charges and the R group has a partial charge. While it is tempting to simply assume the carbonyl is fully negative and the amino group is fully positive, it is important to understand why, because this isn't true for all cases, and understanding this concept will also help find the charge of the R group. To continue, we need to know the type of charges that each group can have. This is because the type of full charges varies between groups. Another way to say this is that the range of charges each group can have are not always the same. For me, this isn't the most scientifically accurate way to look at this, but I like to think for each group there's a quote-unquote negative or basic version and a quote-unquote positive or acidic version for the charges that it can have. For all amino acids, the carbonyl group can only either have a full negative charge as its basic version or no charge for its acidic version. The amino group can only either have no charge for its basic version or a full positive charge for its acidic version. The R group is a little tricky. And depending on that R group, the charge it can take on varies. R groups that can take on full negative charges include aspartate and glutamate. R groups that can take on full positive charges include lysine, arginine, and histine. The negative R groups are similar to the carbonyl group in that it can only be either negative or no charge. And the positive R groups are similar to the amino group in that it can only be either no charge or positive. Since the question states that the amino acid is glutamic acid, a derivative of glutamate, we can also label that on our illustration. Now we know that since the carbonyl is on the left side, or the quote-unquote negative basic side of the pH range, we know that it takes on the negative or basic form, which is the full negative charge. Since the amino is on the right side, or the quote-unquote positive acidic side, we know that it takes on the full positive charge. For the R group, its charge only spans the range of -1 to 0, or no charge. It is unable to reach a positive charge, and we know that because it is a glutamate derivative. In order to find the exact charge value, we now have to use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is really important. I highly recommend committing this equation to memory because it's something you're going to consistently use in homework and on exams. It is pH is equal to pKa plus the log of base over acid. Again, this is similar to before where I like to call basic version as the negative form and the acidic form as the positive version. It's not scientifically correct, but it's something that works for me. Many of the values are given, so we simply have to substitute those numbers in. The base form of glutamic acid, R group, would be a COO-, which has a full negative charge, and then the acid form of the R group would be a COOH, which has no charge. At this point, we would just work out the math. Now we get to the 4 equals COO- over COOH. The important step here is to know that the 4 signifies a ratio between the base and acid concentrations. This can be rewritten as 4 is equal to COO- over COOH, and then the 4 would be over 1. From this, we can cross multiply and get 4 concentrations of COOH is equivalent to 1 concentration of COO-. Furthermore, something you should know is that the concentration of the acid form and the base form should equal 1. Now with these two, we have set up a system of equations. From here, we would just use some algebra and we get 5 COOH is equal to 1. Dividing both sides by 5, we get the concentration of COOH to be 1/5, which is another way of saying 0.2 or 20%. Now that we know this, we can also deduce the concentration of the base form, COO-, to be 4/5, which is 0.8 or 80%. Now, we are trying to find the charge, so since COOH has no charge, 20% would be 0, and since COO- is negative, 80% would have a full negative charge. Together, the R group could be set up as 0.2 times 0, the no charge, plus 0.8 times -1, which is the full negative charge, and working out the math, you would get -0.8. This would be your charge for the R group. Now that we have all the charges for each group on glutamic acid, we can find out the total net charge of the entire amino acid species at a pH environment of 4.8. The carbonyl group is -1, the amino group is +1, and the R group is -0.8. Since the amino and carbonyl groups cancel out, you get a total net charge of -0.8.